Yeah, and we can see your mouse.
Okay.
Yeah, then we can start.
Sure. Hi everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all very much for joining. Our seminar is generously sponsored by 2 Sigma. We greatly appreciate it. Thank you, 2 Sigma. I'm very honored to introduce our distinguished speaker today, Professor Mengdi Wang from Princeton University. Professor Wang is an associate professor at the Department of Electrical Engineering and the Center for Statistics and Machine Learning at Princeton University. She is also affiliated with the Department of ORFE and Department of Computer Science. Prior to joining Princeton, she received her PhD in Electrical Engineering and Computer Science from MIT in 2013. Advised by Professor Dimitri Bersikas. Professor Wang has made many fundamental contributions to data-driven stochastic optimization and applications in machine learning and reinforcement learning. She has received many prestigious awards, including the Young Researcher Prize in Continuous Optimization of the Mathematical Optimization Society in 2016, the Princeton Seeds Innovation Award in 2016, the NSF Career Award in 2017, the Google Faculty Award in 2017, and the MIT Tech Review 35 Under 35 Innovation Award in 2018. Today, she will talk about on the statistical complexity of reinforcement learning. And please join me in welcoming her.
Okay, thank you, Joanne, for the very nice introduction. And so this is my first time doing an online seminar, so I'm super excited. Okay. Okay, so does the slide work?
Seems not. It seems a black screen.
Okay.
Oh,
now
it works.
Okay. So let me start. So let me first thank the organizers for doing this very novel and exciting seminar series, and I'm personally learning a lot from the talks. So I'm going to talk about the theory of reinforcement learning, and so hopefully I will. So I think the main message I want to talk to you is this emerging field of reinforcement learning is really benefiting a lot from data science. And there are a lot of questions about how to optimally use data and how to optimally estimate statistical confidence. And a lot of data science questions arise in the field of reinforcement learning. And there are also a lot of open research questions. Okay, so I want to basically sample a number of theoretical results about the statistical complexity of reinforcement learning. And I'll particularly talk about the use of regression in RL. Okay, so this is joint work with my students in Princeton and my colleagues at DeepMind and UCLA. Okay, so first, I'm sure everyone knows reinforcement learning because it is like the buzzword of the AI community today. So RL has achieved, substantial empirical successes, and especially in domains where we basically have infinite amount of data. By infinite amount of data, I mean like domains like computer games or Go's, in which basically we can simulate the game and we can get as much data as we want. But however, we do want to be able to expand the theory and method for reinforcement learning to broader applications where there might be less data available. Okay, so we do care about data availability and we care about sample efficiency of reinforcement learning. Okay, so I want to discuss several basic theoretical questions about reinforcement learning. So the first one is a very simple one. So consider that we want to estimate the optimal policy for a reinforcement learning task. So this is perfectly fine as an estimation problem. And let's say that we can generate sample state transitions from some generative model. Consider that we have a simulator of the system. So we can just draw samples from the simulator. So I think a 101 question is, okay, now we want to get a near optimal policy. We want to estimate this policy and how many samples are necessary and how many samples are sufficient. So this is a very basic question, and this is a very basic question if we pose policy learning as an estimation problem. Okay, so let's review the model for reinforcement learning. So the most basic model is Markov decision process. So let's consider this very basic case in which we have a finite set of states, which we call it this capitalized S. We also have a finite set of actions. And at every state and action, we have a reward. So the reward is a function of state and action. And also, the system evolves randomly. So conditioned on some state S and action A, the system is going to evolve to a future state with a probability distribution. So once we have specified the reward function and also the transition probability distributions, we have specified this full MDP model. And in this case, the optimization problem is we want to find a policy pi. We want to maximize over all policy pi's. And we want to maximize an objective function, which is defined by the expected sum of cumulative rewards, of discounted cumulative rewards. Okay, so this is, I would say, the most simple model. And we call it tabular, meaning that we don't really have any structural assumption. We don't have any parameterization yet. Okay, by tabular, we mean that we just have a finite number of states. And we can basically specify the model by using a table of coefficients. Okay. And now let's answer the first question. Recall that the first question is, what is the sample complexity for solving this tabular Markov decision process? By sample complexity, we mean that we want to get an epsilon optimal policy. So this is what we want to achieve. And we're going to find such a policy by drawing samples from the generative simulator. So there exists a series of work on this particular theoretical question. And it turns out that now the answer is almost final. So there exists an information theoretical limit proved a few years ago by some folks at DeepMind. So they show that, okay, no matter what we do, as long as we want to get an epsilon optimal policy with probability, like say 2/3, with a mild probability greater than 1/2, okay? So in order to achieve this, we actually have a lower bound of the sample size. So we need at least this many samples from the simulator in order to get a good policy reliably. Okay, so this is, I would say, information theoretical lower bound. And in the recent, I would say, a couple of years, so it turns out that one can actually match the lower bound. So there actually exist algorithms in which people actually construct an algorithm to draw samples from the simulator. And the algorithm indeed achieve an epsilon optimal policy using such sample size. Okay, so I don't think it's important to look into the details of these algorithms. I think the first order critical theoretical question is, do we know the necessary and sufficient sample size to achieve a good policy? And now we know, because the lower bound and upper bounds, they are almost the same. Okay, so now that this very basic statistical question is already answered, we want to move on and ask deeper questions. Okay, so one thing that we actually hate about tabular MDP is that whenever we try to just enumerate all the states, the algorithm is not going to be tractable at all, because the state space, this capitalized S, is usually something too big to be enumerated. So the state space is usually something that blows up exponentially in the dimension of the state variables. And the size of policy space is an even bigger number. Okay, so having that this S could be huge in mind. And now if we look at the known theoretical results for the tabular case, we realize that both the upper and the lower bounds are too pessimistic. So they are good theoretical results, but they are not useful enough because those results do depend on this number of states, S. So those results do depend on enumerating all the states. Okay. So further, we want to consider, okay, can we estimate the optimal policy by adding a little bit of structure? So one common practice is, okay, so I could have a huge number of states. So in the game of Tetris, so each board like this could be one state. And the total number of states could easily be, I think sometimes, the total number of states could be like 3 to the power of 200. So something huge, something that we can never enumerate. But however, we don't have to enumerate all possible states in the Tetris game. We can try to vectorize this board of the game into a finite vector, which we call them features. And it turns out that I think almost 30 years ago, without even using neural network, so researchers at that time can already solve the game of Tetris pretty well by using only 22 features. And the features are just selected by hand. So the features are something that's very intuitive. For example, what is the current height? And also, what is the profile of the top level of the Tetris board? So there are just a number of very intuitive features. And one can try to improve this by saying, hey, instead of handpicking the features, we can use neural network to learn the features, to learn a more complex nonlinear representation. And one can try to, again, instead of enumerating all the states, one can try to use some learned representation of the neural network to predict values of states. And there are many other methods in which people can try to do some dimension reduction first and run some random feature selection first to learn those state features. So basically, vectorizing a raw state into a finite dimensional feature is a common practice. And also it's a popular research subject in the literature. Okay, suppose that we have already vectorized the state of Tetris into a vector. So now what do we do? So recall that whenever we try to solve the Markov decision process, most algorithms involving estimating some value function of this form. So this value function describes the cumulative sum of rewards conditioned on the input state by following some policy. And basically any reinforcement learning algorithm they always involve iterating over some value functions or estimating some value functions. Okay, but now the problem is, okay, if we do not have additional structure, then simply representing this value function would require enumerating every single state. Then we get this high complexity because of the large number of state S. So now suppose that, okay, we have a number of features, say that they're just hand-picked features. So it is a common practice to try to approximately represent this value function, which lives in a high dimensional space. But we can approximate it by using a linear combination of features so that eventually we try to approximate a high dimensional function using a lower dimensional function class. So this is the simplest value function approximation scheme. Okay. So what is this really doing in solving the MDP? So I want to give you some high-level idea of what's really the structure of Markov decision process. So I'm sure many of you know about the Bellman equation. So here I wrote down one example of the Bellman equation, which is a specific form for the average reward infinite horizon undiscounted problem. Okay, so basically learning the optimal policy requires us to solve this system of nonlinear equations, which has to hold for every single state in the state space. Now that solving such a big system is going to be both computationally hard and sample inefficient. So we try to change a problem in a way that is easier to understand. So there's a very interesting relation between the Bellman equation and optimization. So it turns out that the optimal Bellman equation, which is the optimality principle for Markov decision process, is equivalent to a saddle point problem, a minimax saddle point problem. So this nonlinear equation, right here, is equivalent to a minimax problem. And this minimax problem involves primal minimization in the space of all value functions and the dual maximization in the space of the stationary state action occupancy measure. Okay, so there's a very interesting duality between value functions and the invariant measure of policies. Okay, and there's a longer story here, which I don't think I have time to cover. But now what's really interesting is, now if we think about solving Bellman equation with functional approximation or with lower dimensional structure, we can try to think that, okay, originally we have this high dimensional system of nonlinear equations, but in order to solve it, we can imagine that this is really a mini-max problem over two space of functions. And now if we have prior knowledge, or maybe we use non-parametric kernelization, or maybe we have a general family of functions, but we can always think that, okay, now we want to solve this high dimensional minimax problem over maybe some lower dimensional constraint, which could be a nice manifold. Okay, and in the special case with linear model and the featureization, this high dimensional minimax problem can be reduced to actually a small dimensional minimax problem over finite parameters. And okay. And now that we have already shown that one can reduce a high dimensional Bellman equation into a high dimensional saddle point problem, which further reduced to a lower dimensional saddle point problem. So this actually enables a class of algorithms for solving this kind of problems. And there are a number of results. And basically one can show that, I think this is important message. One can show that by constraining the space of primal and dual functions, one can reduce the sample complexity from depending on the number of states and number of actions here to the number of parameters in the parameterization. Okay. So that's basically what I wanna discuss regarding the first question. So the sample complexity for learning the optimal policy depends linearly on the number of states if we do not have any parameterization. But if we have some nice functional approximation, then we would expect that the sample complexity reduces to the dimension of the parameterization. And the intuition is really that we are reducing a high dimensional minimax problem into a lower dimensional minimax problem. Then the dimension just reduced very intuitively. Okay, so now I want to move on to the second topic of my talk. Okay, so, what if we are considering a more practical scenario? Suppose that we have some data set generated by either our own learning algorithm or just some other expert. Okay, so we have some past experiences. And we want to rely on those past experiences to be able to predict what would happen if we implement a new policy. Okay, so this is a very basic question in batch data reinforcement learning. So it arises a lot, for example, in biomedical applications. We might be talking about clinical records for treating some disease, or we might be talking about maybe gene expression measurements from some limited cell experiments, or the data could be just results from a number of clinical trials. So in all those examples, we really have limited data. And a very practical question is, okay, we have some batch data, which is not a lot, but we want to do our best with the data. And say that let's say that we are running clinical trials. Now we want to implement a new trial or a new treatment policy. But it's important to predict what the policy would behave before implementing it. So we want some prediction. Okay, so this problem is rigorously known as the off-policy evaluation. By off-policy, we mean that we are only relying on batch data. We cannot run the policy that we want to evaluate. Okay, so the setting is as follows. So suppose that we have a data set, let's call it just D for data. So D stands for a collection of state actions, reward state transitions. Sorry, I missed a prime here. This should be S prime. So just some state transitions. So it could be just data collected from past records by another expert. Or the data could be collected from some simulator. But we're not making assumption on how the data is collected. So now our goal is, okay, I have some data, and we want to estimate a single number. So we have a target policy pi, so which is a new policy that we plan to implement. Okay, but this new policy, what hasn't been tried before. So we want to evaluate the value, the cumulative rewards to be obtained under this new policy, conditioned on a given initial distribution. Okay, so this is a very basic estimation problem. We have a single number to estimate. Okay, and also I'm going to call I'm going to let pi bar be the behavior policy. So whatever policy that generated the data. So the behavior policy and the target policy can be completely irrelevant. Okay, so however, we don't know the model of the problem. We don't know the underlying transition functions. We don't know the closed form reward function. We also don't know what is the behavior policy that generates the data. So the only input we have is the data set. So, so this is a very basic question, and also it's actually, I think, one of the most critical questions for batch data RL, because in applications in which we do have limited data, one cannot expect to be able to solve the full decision-making problem with confidence. So it turns out that it's actually already a hard problem to try to predict what happens with a new policy, because this new policy is not the policy that generated the data. Okay, and also suppose that we can solve this task, say that if you give me a data set, I can reliably predict the behavior of every single new potential policy. So if I can solve this task, now we'll be able to say that, oh, okay, I can predict a bunch of policies. So we're just going to compare them and pick the best one. So if we can solve this problem, all the policy improvement and optimization problem will be trivialized. Okay. So let's say, what can we do to solve this problem? So if we think about the problem, we quickly run into a technical challenge, because the sample rewards in the data set are generated according to a target policy. So this is the conditional probability for choosing action A conditioned on state according to the behavior policy. Okay, so if I want to get an unbiased estimate for rewards from this state for the new policy, then we want to basically reweight the sample reward from the data, because this reward will show up with a different probability according to our new policy. So we want to reweight samples. But there's another challenge. We don't know this pi bar, so we cannot even compute this value. And the problem becomes more complicated because not only does action show up with different probability distributions under a new policy, the states also occur with a different distribution. So then one might need to even estimate the ratio between two probability measures, one corresponding to the target policy, one corresponding to the behavior policy, which we do not know. So it turns out that we have to estimate a bunch of things in order to estimate one single value. And there are a lot of efforts that try to improve this important sampling mechanisms to relax assumptions and to get better convergence rate. Okay, but as you can see, whenever we try to do important sampling reweighting, we have to estimate quantities that are unknown, and this will make estimation error potentially large. And also there's really little theory beyond the basic case of tabular MDP, which unfortunately suffers from the curse of dimensionality. Okay, so I'm going to show you an alternative approach. And we want to do off-policy evaluation with function approximation. Okay, so you might ask, okay, so why do we need function approximation for estimating a single value? Because if we want to learn a value function which is high dimensional, maybe I want to parameterize this value function. But now we only want to estimate a single value. Why do we need function approximation or additional assumption? So the answer is very simple. So we do need function approximation to do generalization because we have limited sample about a subset of states, but we really have a huge state space. So we want to make the best use of our data by making sure that the sample that we observe from one state provide us some knowledge about other states. So we want to use function approximation for generalization, which should be able to help us get more robust estimator. Okay, so we're going to make this assumption. So we're going to say that, okay, I'm going to approximate all the Q functions of interest within a family of functions. So this could be a large reproducing kernel space, for example. And we're going to assume that the Bellman transition, not the Bellman, the transition operator of the Markov decision process under policy pi actually is closed within this family of functions. So this is a typical assumption when we use function approximation. Okay. So basically, we're going to assume that, okay, all the Q functions we care about belong to a particular family and is sufficient to approximate Q functions within this family. Okay, so now let's return to the OPE problem. And we have a very simple solution. Okay, so let's say that we want to estimate all the Q functions of the target policy pi. And so we start with the last Q function, which is 0. Say that now I want to estimate the second to last Q function. Okay, so we have a family of functions. So I'm going to do regression by finding the best fit little f from this family of functions. And I'm going to fit this function to minimize the squared difference between the one step forward value of the Q function at the next stage. So basically, we're going to say that, okay, condition on state S and action A. Now my data gives me a random transition to this S prime. And then I'm going to use this S prime to compute the expected value based on the Q function that we have already estimated. So this is a very simple mechanism in which we simply recursively estimate all the Q functions by regression. And we could add a normalization term if needed. So finally, if we have estimated the Q function at stage 0, we can easily compute the value function at a pre-specified initial distribution according to the known target function. Okay, so this is really just approach with recursive regression, and there's really no optimization there at all. Okay. So I want to show you that this very simple regression-based approach turns out equivalent to a plug-in estimator. So by plug-in estimator, we mean that we can view the procedure equivalently as, let's say that I have a data set. So I'm going to find the best fit of the transition operator by fitting the transition operator onto the data set. And now we have function approximation. So this transition operator actually takes form that is an operator that works only in the family class. So we have an estimated transition function, and we have an estimated reward function. And now, in order to estimate the value function, we simply take those estimated quantities as if they are real, and then we just compute the corresponding estimate of the value by plugging in those estimated p hat and r hat. And it's straightforward to see that the two approaches are equivalent. So recursive regression is equivalent to estimating the model first and then using it as a plug-in estimator. Okay, and one can further show that not only do those two estimators are equivalent, they are also equivalent with the best performing importance sampling estimator. So there are actually a strong equivalence, and it's like importance sampling is the FIT-Q iteration in the dual form. There is some subtlety there. Okay, and also this is what the estimated transition distribution look like in the case of linear function approximation. So we can see that we are really estimating the conditional mean embedding of the transition operator. And as long as we can estimate the transition model, we can solve it using any MDP algorithm. Okay. So that's enough for the algorithm. So let's talk about, okay, what can we show statistically? So we have showed two estimators. And one can show that actually the proposed estimators, they have pretty good statistical error. So in particular, this statistical error between the estimated value of the new target policy and the ground truth scales with this quantity as an upper bound. And further, we also show that this policy evaluation estimation error is also a lower bound by using a minimax analysis. So what does this statement mean? So basically, we're saying that as long as we're trying to estimate the value of a new policy, this infimum means that no matter what algorithm we use to do this estimation, and super means that there always exists some hard problem such that the estimation error is always of this order. The estimation error cannot be smaller than this. So in other words, there is an algorithm achieving the theoretical lower bound. So we have shown that the policy evaluator is actually minimax optimal. So we cannot do better than this. Okay, so I think a very basic message is regression is actually efficient and statistically optimal for this off-policy policy evaluation task, which is nice because we all know regression. Okay, so I'm going to say a little bit more about this quantity here. So in the error bound, we have this statistics right here. So the error is on the order of 1/square root of sample size, but also depends on this statistics. So this statistics is what we define as a variational divergence, which is restricted to the function class that we started with. Okay, so this statistics quantifies how does the target policy differs from the distribution of the data. And we're not talking about point-wise divergence. We're talking about the divergence that are only meaningful to our family of functions. So this is a restricted divergence. Okay, so for example, if we don't have any function approximation in the tabular case, so this restricted chi-square divergence reduces to the typical Pearson chi-square divergence, and it could scale with the number of states in the worst case. But if we have some function approximation, for example, if the Q function class is a kernel space or just a linear space, then one can bound this chi-square divergence by using a relative condition number of covariance matrices. So they can be easily checked, because once we have the data, we can easily just check the covariance matrix. So we will be able to know the quality of our estimate by simply looking at covariance matrices and their relative condition number. Okay, so basically, this statistics quantifies the hardness of problem, which is an interplay between the distributional mismatch as well as the function, the family of functions we're using for approximation. Okay, and there's a lower bound analysis, and let's skip. Okay, so that's the second part of my talk. So finally, I want to just spend a little bit of time talking about how can we carry out this regression idea for online learning and reinforcement learning. Okay, so now we are switching the gear. So we had two previous topics. The first one is the simplest, in which we have a generative model, meaning that we have a simulator and we can just generate samples in whatever way that we want. And in the second part, we talk about, okay, I have a batch data set and we want to make the most out of it. So in those two cases, there's no exploration at all. And now we can consider a harder case, which is we want to do online learning. We don't have a simulator, meaning that we have to learn by paying a real price for observing new information. Okay, so this setting is what we call an episodical reinforcement learning problem. And let's say that we have a control problem or just a computer game involving 8 steps. So we're going to be repeatedly playing this game for multiple episodes. And hopefully our learning algorithm will learn something about the optimal policy as it collects data, and maybe it will converge to the optimal play eventually. Okay, and this is a harder problem because we can never guarantee that the learning algorithm will visit all the states frequently enough. And this is in contrast with the two previous settings we talked about. Okay, and in this case, if we have to do online learning, then we are going to measure the efficiency of online learning using a notion of regret. Okay, so say that my algorithm is K. So I'm going to use this algorithm to start playing the game, starting from the first episode, little n equaling 1, to n, big N episodes. So for every episode, the algorithm K is going to generate a bunch of state and actions, and we are going to collect the sum of rewards on the sample path generated by the algorithm. So this is the collection of rewards to be obtained by the algorithm. And we're going to compare this value with the optimal value that one can expect to earn if the optimal policy is known. So this difference is always non-negative. So we are going to consider the sum of this difference. We call this the cumulative regret of the learning algorithm. Okay, so there are many theoretical challenges here. So for example, if you are familiar with the bandit literature, so RL is harder because if the algorithm makes a wrong decision at the beginning of the episode, this single wrong decision will have a longer term effect on the future rewards. And also, all the rewards at the samples are generated on the same sample path, so there's a lot of data dependency. So this is, I would say, one of the most exciting theoretical open questions in RL. Okay, so I'm just going to show you how to do regression. So I'm going to just, let's say that we're going to just do linear regression as the very simple illustration of online learning in RL. So suppose that we already have feature maps so that we can vectorize state and actions into features. We can also vectorize states into features. So now, although we still have a high dimensional transition probability distribution that we do not know, but we can actually approximate this unknown high dimensional or even infinite dimensional quantity by embedding it into the feature space. And there's a matrix embedding, which we call it the transition core, M star. Okay. And by using this very basic linear model, we can always embed a complex transition function using a finite but maybe large dimensional matrix. Okay. And now we can do online learning. And we call it matrix RL because it's really a simple matrix-based iteration algorithm. So apologize for the heavy notations. So let's just maybe just read the red lines. So we can always try to estimate the matrix embedding of the transition function by doing some form of regression. Whenever we have data, we can estimate by regression. And also, whenever we have data and we have regression estimate, we can always find a confidence ball around the matrix embeddings. So all of this are basic statistical analysis. So now that we have data and we have our estimated embedding model and we have a confidence set, we can do optimistic Q function estimate by always optimistically believing that the Q value we are going to get will be corresponding to the best model in the confidence set. And as long as we're doing this optimistically, we're also going to use the estimated Q functions greedily in choosing actions in the next episode. So this is a very basic framework for model-based reinforcement learning. Okay, and as you can see, it heavily relies on regression to estimate the transition function and building confidence ball. Okay. And another way to think about this is we are really trying to iteratively estimating Q functions by doing regression over previous estimated value functions. And the confidence set will place into this estimate as an additional optimism bonus to make sure that we sample actions that are less representative in the data set with more actively, so we can guarantee exploration. So the brief theory is, if we do this matrix embedding and model estimation, we can reduce the regret of exploration in RL, which takes this form, into a smaller regret that depends polynomially on the dimension of the feature space. Previously, it depends on the number of states and actions in the raw representation. Okay, let me skip this. See if I have time. Okay, so I think I might have like 5 more minutes. So finally, I want to show you that regression is really powerful. We can do regression in a more general way to do end-to-end training of RL agents. Okay. So let's think about the role of regression. So I was trying to convince you that we can embed the transition function into a matrix. So in other words, this model is really saying that whenever we have a state and action pair, and we have its featurized vector, okay, if we have a linear model or a matrix embedding, then we can try to use this input to predict what could happen in the next state. So this matrix embedding idea I talk about is one way to parameterize this prediction problem. Based on the current state action, we have a model to predict either the next state or features of the next state. Okay. And as long as we can always predict what happens in the next state, then we can eventually solve the problem. Okay. But however, so in practice, so we run into a practical issue. Because in practice, we can definitely try to fit this prediction problem into a simple linear model or a more complex reproducing kernel space, or we can fit a deep learning model. We can fit even a recurrent model to do this task. But a practical challenge is, before we fit this into a model, we have to specify this. We have to specify what we want to predict. For example, in Atari games or in more complex video games, it's actually very common to just train maybe just an RNN to try to predict the raw next state, which is the raw pixel image of the next state based on the current state and action. But this is not trivial in practice. So the challenge is, if we want to do pixel-to-pixel training, then we're going to predict a big quantity, the entire image, for example. And we do know that much of the images are not relevant to solving the game. So we are going to be fitting the model to predicting many quantities that are not useful. And also, if we want to predict a multivariate target, maybe the raw pixel image, then we have to really choose the correct loss function. In other words, we have to scale the target in a way that we make sure that the loss captures what matters in finding the policy. And also, if we try to predict a complex objective, then there's a lot of computational overhead. Tuning parameters is non-trivial, is hard, and also generalization could be hurt. Okay, so basically now we want to say, hey, can we do better than this? What if we do not know this phi? I don't want to predict the entire S prime, or I don't know a good set of features that I want to predict. Can we predict something that is useful only for the reinforcement learning task? Okay, so in parallel to our work on this, so it turns out that there was another very related motivating example, which is the mu0 by DeepMind. So mu0, I believe it is the state-of-the-art algorithm in the domain of solving Atari games. So it is one single algorithm that can work on more than 60 games. It also works on the game of Shogi and chess and Go. So you might say, okay, so we know that Atari games are simple, and the AlphaGo already solved the game of Go. So what's interesting about introducing a new algorithm here? So the point of having a new algorithm is basically researchers hope to get one single algorithm that can generalize to multiple tasks at the same time. Before this algorithm, AlphaGo was customized to solving the game of Go. And there are other deep RL algorithms that has to be customized to particular Atari games. So we don't want to customize an algorithm to solve every single game. We want one algorithm to solve them all. So it turns out that mu0 achieved this. And achieved this by doing model-based reinforcement learning, because all the games have different rules. So mu0 will learn the rules of the game first, and it's going to do optimistic planning and exploration by using the learned model. And what's really interesting is here. So in order to learn the rule of the game, mu0 doesn't try to predict, for example, board of Go or this image of Atari. mu0 only tries to predict value functions of the next state and policies of the next state. Okay, so that's why it can generalize. Okay, so in parallel to this practical advance, so we try to make this idea work for general model-based reinforcement learning. Okay, again, so this is a more abstract framework for model-based reinforcement learning. Okay, so in order to do exploration, we always wanna estimate the model and build a confidence set of the model parameters based on the data. And then we use the confidence set of the learned models to do optimistic planning. So this is always the framework of model-based RL. And in this case, we consider a general family of transition models. So it could be just any set of transition models. And we want to answer the question is, okay, so the model itself is a collection of transition distributions. So the first question is, do we actually need to recover all of these transition distributions? It seems hard, unless we make strong assumption on the models. And secondly, can we do predictive control? Meaning that, can we try to predict useful quantities, but not predict the actual next state? So we don't want to do raw pixel, we don't want to predict the raw pixel image. Okay. And thirdly, can we use value functions for self-training? And how do we do that? So the answer is yes. Okay, so the algorithm is pretty abstract, and I only want to implement the key difference. So the key difference is this step. We call it value-targeted regression. So whenever we try to fit the parameter of our transition model to the data, we don't try to fit the data to minimize the prediction error in the raw next state. Instead, we try to predict the value of the next state. So the value of the next state is already something that has been computed by the algorithm beforehand. So this is the only difference. We try to fit the model, but when we fit the model, we are targeting only on the value instead of some other representation of the states. And what's interesting here is that the value function, this y here, the regression target, which is defined here, the value function is the estimated value of our next state. So v hat is a function computed, learned by the algorithm. It's not even the true value. So somehow the algorithm is doing self-training. It learns a value which could be inexact or even way off. But it's going to use this learned value to reinforce its model estimation by regression only onto this value target. And the rest of the algorithm is really just a special case of the general framework. Okay, so we do value targeted regression to estimate the model, and then we build confidence set around it, and then we use it for updating the policy and further exploration. Okay, so this is the, I would say, an informal statement of the theorem. So it turns out that the regret for this learning algorithm is nicely bounded. And since we're talking about a general family of models, so the regret is determined by some notion of eluded dimension of the family of functions, and also a metric entropy of the family of functions. And in the case with linear models, it recovers the known best regret by using linear model specific algorithms. Okay, so I think in short, what we want to say is that this very general approach using value targeted regression is actually sufficient for efficient exploration, which was something we didn't expect when we work on this. So because we are trying to learn a model by fitting it onto a self-defined target, and turns out that this is enough. Okay, and okay, now back to this. So basically, I think the abstract theory I just presented in some way validate that the approach of mu0 is valid. It's okay to not try to predict this raw image or this raw image. It's okay to simply try to fit the learned model onto the estimated values. So this is an important prerequisite in order for one algorithm to be able to generalize to a number of tasks with diverse state representations. Okay, so finally, this is a summary. So basically, we talk about three cases. In the first case, we have a generative model, so we can simulate samples from any initial distribution. And in this case, the minimax optimal sample complexity is already known. And if we have a nice functional approximation like a linear model, then this big S reduces to a smaller dimension, and big A also reduces to a smaller dimension. And secondly, if we are given a batch data set and we cannot do further simulation or we cannot have further data, and it turns out that regression with iteration is sufficient to get the best estimator for evaluating the value of a new policy that hasn't been implemented. And this error depends on a restricted chi-square divergence. And this divergence could be small if the family of functions is well behaved. Okay, and thirdly, if we want to do online exploration in reinforcement learning, it turns out that there's a principal way for estimating the model and using it to do optimistic planning. And also it turns out that we don't have to choose the regression target specific to any particular game. There's a principled way to choosing the regression target by simply using the estimated value. And there's a nice theory about it. So I think the very interesting news here is that regression actually works. So regression enables reinforcement learning not only in practice, but also in theory. And there are definitely more open questions to be solved. But I think what people already know about statistical regression, statistical supervised learning, will find very nice use in the domain of theory of reinforcement learning. Okay, so that's my presentation. Thank you very much.
Okay, let's thank Professor Wang again for the great talk. So there have been over 1,000 people participated in the seminar just now across different platforms. So maybe let's look at some questions raised in the Q&A section. So the first question, Han Zhang from MIT asks, is there a way to test whether a feature space is good?
Okay, so that is a very, very good and deep question. So I didn't talk about it at all in my talk, but I think so my group and as well as many other groups are actually working on representation learning for RL. For example, how do we identify the feature space purely from data? And how do we do model reduction and dimension reduction in the feature space? Do we want 100 features or 10 features? So I think there are, so this is, I don't have a simple answer to this question. So I would say that there are a lot of ongoing, past work and ongoing work on representation learning for RL, and people are trying to resolve this question.
Thank you. So another question from Han Zhang. So it seems that part 1 and part 2 assumes offline learning environment that is not using online data. And part 3 studies online learning and no pre-collected data. So could you please provide some deeper thoughts on how offline learning results can be connected to online learning results?
Okay, so that's also a very good question. And I believe there are many people in the audience or in the organization committee who are expert in this. So basically, for example, I did show you, I don't know, can you still see the slides?
No.
No, okay. Sorry about that. Give me 10 seconds, okay. Okay, can you see it now?
Yeah, yes.
Okay, so this is one particular algorithm for model-based RL. And as you can see, so the key step is to estimate some parameter of the model or just some unknown parameter, and then build a confidence set around it. So there are many different ways to do this. I mean, depending on what is the assumption and what are other practical constraints. But basically, this is really about estimation of some unknown quantity from a given batch data. So if we can answer all the statistical questions in batch RL, then we will have the best, sharpest confidence bound for this task. And that will be useful for getting sharp regret bounds in online RL. So basically, I think in every single step of adaptive online RL, we are analyzing a batch data, which is a collection of past experiences.
Okay, thank you. So another question from Ahmed. So could you please give an example of function class that satisfy the expressiveness assumption for arbitrary transition dynamics? I think maybe he or she is talking about the linear, the offline, the second problem, where you assume that the for any policy pi, the t pi, the Bellman operator is closed with respect to the function class.
Oh, I see. Oops, sorry. Okay, so that's also a very good question, and there have been like philosophical discussions around it. So whenever we are using function approximation, so the function approximation means that, okay, means that we are trying to do this prediction. Can you see my mouse?
Mm-hmm. Yeah, yes.
Okay, so for example, if we are trying to use a matrix embedding to model the transition operator, or if we are using some family of functions, then in other words, we're saying that we can predict the expectation of some functions of the next state. So this is an equivalent representation of the same statement, because this prediction task is all about approximating the projection of the unknown transition operator in a well-defined family of functions. Okay, so I think philosophically speaking, when we talk about closureness of the Bellman operator, we are saying that we have some family of functions in order to do some variant of this prediction, and we have to rely on this. And another example is we can think about this psi as a collection of an infinite number of basis functions. For example, in continuous control, all the value functions and all the states, they are continuous valued or even infinite dimensional. But in that case, we can try to approximate those unknown functions by using Gaussian process or by using reproducing kernel space. And in that case, we can view that this psi could be just a collection of all the basis functions or the collection of truncated basis functions. And in other words, instead of saying that we can predict this relation, we can also say that we're trying to embed this high dimensional, infinite dimensional quantity using non-parametric function approximation. And then if we want to say, okay, what if my model doesn't satisfy this, we should be able to use classical results, it may be non-parametric function approximation, to say, hey, if this assumption is misspecified, then our estimator will incur an additional loss. And it turns out that there exists rich, I would say very rich earlier literature on how those basic algorithms would behave if the model is misspecified. And that should be something to be really careful about when we actually implement the algorithm.
Okay, thank you. So another question from Ahmed is that could the Minimax results for the fitted Q-learning for policy evaluation problem be extended to the control case?
Okay. I think I would say yes and no. Let's come back here. Okay, so this is the Minimax error, right? So I think there's I would say a subtle but quite important difference between batch policy evaluation and batch policy optimization. So what happens is, if we look at this error, so we have this statistics, right? This statistic is like a divergence with a dual definition. But what it's really saying that is this statistics depends on the target policy. So if the target policy has a distribution that happens to be close to the distribution that generates the data, this statistic could be close to 0, even if dimension is super high. So I'm trying to say that this Minimax error bound depends on the target policy. So it is true that one can try to extend this to policy optimization. But to do that, one needs to be careful that we actually need to make sure that the assumption, we need to make sure that the data we have is sufficiently good to represent all the policies that are candidates for the optimization problem. For example, if my optimal policy turns out to be far away from the data, so this value could be very big. In that case, my data is simply not good enough for us to learn about the optimal policy. So I would say that in general, unless we make very strong assumption about the data, it will be hard to say formally that, okay, this is what we can achieve by batch policy optimization. But one might be asked more practical questions like, if this is the data I have, and I want to have a good policy, which doesn't have to be optimal one, but it has to be reliable enough with high degree of confidence, then can we find a robust policy by doing batch policy learning? So I think one does need to rephrase the question carefully in order to make sure that we can only answer it based on the data we have. And the data we have might not be enough to solve the policy optimization problem.
Okay, thank you. So another question is that do you think that that these regression methods can do benefits to the imitation learning problem, and compared with the Gale framework, can these methods shed some light to the generative models?
You mean just imitation or imitation for inverse RL?
Imitation learning for, say, Gale, the generative adversarial imitation learning.
Yeah, so when we tried that, so first, I believe there's still a gap between the theoretical result and the imitation and inverse RL algorithms like Gale, or like this. I think there's an advanced version of Gale. Mm-hmm. So I do think that some of the results here are in similar spirit with Gale, because whenever we're trying to fit a function into the data, in some way, this fitting procedure is already doing a model estimation implicitly. And also there are equivalent forms of the fitted Q equation that happen to coincide with some minimax optimization problem. I think that formula could be closer to the objective of Gale. And as for imitation learning, I think that's different question. So in imitation learning, that depends on, for example, in this batch policy evaluation problem, we actually do not know the behavior policy. But however, learning the behavior policy could actually be a harder problem than estimating the value of a new target policy. So you can see that, for example, the behavior policy could be a complex function, but if we only estimate one single value or a few values, then the complexity might actually depend on a smaller dimension. So I think there are a lot of subtlety here, and this really depends on, for example, if we have a well-defined loss function for imitation learning, then that could be done. And what they have in common is this distribution mismatch term. So for example, if I have some data generated by a known or unknown policy and we want to learn from it. So what really happens is we have data from one domain and we want to learn from those data to apply it to a different domain. So this distributional mismatch will show up, I think, in all of these different applications. It also shows up in the classical transfer learning theory. So I do think something like this will definitely show up in the theoretical analysis of Gale.
Okay, thank you. Maybe let me ask the last question. So in the last part of your talk, you are talking about how to use regression to do exploration. So I was wondering, when we have a confidence set for the model, when the model is parameterized by some parameter theta, how do we do optimistic planning?
Okay, you mean like optimistic planning for a general model?
Yes, for general parameterized model, how do we ensure that we can select the optimistic version of the optimistic model from the confidence set?
Okay, so that's a great question. So I don't have an answer to solving the exact optimistic planning algorithm, but I do believe that I think people are working on this. Like optimistic planning doesn't have to be has to be done exactly, and there are a lot of theoretical and empirical evidences showing that optimistic planning can be done in a randomized way or with some heuristics, and this will have a minor effect on the final regret bound. So I believe there are already papers out there. But I getting back to the original question, so solving the optimistic planning problem is basically equivalent to solving a new Markov decision process with specified input. So computationally, this problem could be hard for a general model because we really don't have any parameterization or low dimensional representation, and this could be hard in general. But in most of the special cases that we care about, for example, in the case when we use matrix embedding for the transition model, actually optimistic planning and it can be done in runtime, I would say, either quadratic or linear to the dimension d. So as long as we have nice representation to the value function, I believe there should be a nice runtime guaranteed algorithm. Most generally speaking, it could be as hard as solving a new problem, computationally speaking.
Okay, thank you. Thank you for answering so many questions.
Oh, thank you, my pleasure. I mean, all the questions are super good.
So maybe let's just finish here, and please join me in thanking Professor Wang again. Also, thanks everyone for joining. We are looking forward to seeing you guys next week.
Okay, thank you very much.
Thank you.